Hello, my name is Brian Moda, and today I'll be going over the strain rosette problem. And I will set up my DocuCam. Give me a second to get this going. Okay. So, the problem I will be solving today is the strain rosette shown is used to measure the strains on a structure made of AIS I302 stainless steel. Gauge A reads 475 microinches per inch. Gauge B reads 200 microinch per inch. Gauge C reads negative 250 microinch per inch. Find my sigma 1, sigma 2, and Tmax. Report your answers KSI for those transformations. Please explain how to use Mohr circle. So I will start off by doing a flowchart. And to solve this, first you use your strain gauge data that is given in the problem, and then from there you're gonna use you're gonna go down, you're gonna use your strain rosette equation, and then you're gonna find your state of strain. So that's the first step, and given is our strain gauge data at A, B, and at A, B, and C. So our given data is at A, it is 475 times 10 to the negative 6 inch per inch. At B, it is 200 times 10 to the negative 6 inch per inch. At C equals negative 250 negative 6 inch per inch. So we need our state of strain at X and Y. So since this A is going at the same through the same axis, our EA equals EX, which equals that value. And for EY, we don't know that, so we're gonna utilize our strain rosette equation. So at B, the strain rosette equation is EB equals EX cosine squared theta B plus epsilon Y sine squared theta B plus gamma XY sine theta B cosine theta B. So this is our equation, and we have our knowns, which is our givens, which are here. We plug in, and if we plug in, we get 200 times 10 to the negative 6 equals 475 times 10 to the negative 6. Our theta B is to respect of x-axis. You go down to your B, which is negative 60. Epsilon Y, we don't know that. Sine squared negative 60 plus gamma xy sine negative 60 cosine negative 60. If we plug this into our calculator and we subtract to the other side, we get 8.125 times 10 to the negative 5 equals point. And then if we get sine squared of negative 60 is 0.75. Epsilon y, sine negative 60 cosine negative 60, that is a negative 0.433 gamma xy. Now for our C, we're gonna leave that as is, and we'll come back to it. We're gonna do the same thing, use our strain rosette equation, but this time for C, and for note-taking purposes, I will write it out. Is the same thing except our theta's change. So our theta c is to respect of x-axis. You go down to b, cross it. So it's negative 60, which is 120. We're gonna plug in our known equations. So EC equals negative 250 times 10 to the negative 6 inch per inch equals our EX, which is 475 times 10 to the negative 6 cosine squared negative 120. We add that, we get epsilon y sine squared negative 120 plus gamma xy sine negative 120 cosine negative 120. So if we plug this into a calculator and we subtract to the other side, we get negative 3.6875 times 10 to the negative 4 equals 0.75 gamma y, epsilon y, sorry, plus that was cosine squared negative 120 equals that. Sine squared negative 120 gives you 0.75, and then sine negative 120 cosine negative 120, that gives you a value of positive 0.433 gamma xy. So here we have two equations, two unknowns. We can just add these two. So I'm going to bring this down. I'm going to add these two. I'm going to add all of it. So I'm just going to bring it down. 6 equals 0.75 epsilon y plus negative 0.433 gamma xy. Here we have a negative positive. This goes away. You add these two. This is 1.5 y equals, and if you add these two, you get a negative 2.875 times 10 to the negative 4. And if you divide this to the other side, my EY is gonna be negative 1.916 times 10 to the negative 4. So we know our EY, and we're gonna use this later. So now we know our EX, which is here, and our EY here, and we need our gamma xy. So to solve for gamma xy, we used the equation 2 epsilon c minus 2 epsilon b over the square root of 3. So if I plug in these numbers, is 2, or epsilon c is negative 250 times 10 to the negative 6 minus 2, our epsilon b is 200 times 10 to the negative 6 all over negative 3. So our gamma xy, you plug that into a calculator and you get a value of negative 5.196 times 10 to the negative 4. That is my gamma xy, which my gamma XY is our shear strain. And then these are just our strains of Y and X. So now that we found that, we can go two approaches. We can either, so coming back to here, sorry. Going back to the flow chart, we can either go this way or we can go this way. And we can utilize generalize of Hooke's law. And we're gonna get our state of stress. And then if we go and use Mohr circle, we get our principal strain. And then we go here, and we can find principal stresses. And then here we can, in this step, we use Mohr's circle, or we can use Hooke's law. So we can go either approach on this. I'm not sure if you can see that, but just to explain this flow chart, my strain gauge data, I was given, use strain Rosette, and I found my state of strain at XY. So here I can either use Hooke's law or use the Mohr circle. I tend to use Hooke's law, then I use Mohr circle because logically it makes more sense for me. So okay. So okay, so here I'm gonna use Hooke's law. I'm gonna start using, so these are values that are gonna come in handy that are from Appendix B. So I'm gonna start using generalize, sorry, I'm out of the thing. Okay, generalized Hooke's law. From generalized Hooke's law, I can find my sigma x and my sigma y. So from Hooke's law, I get my sigma x equals my modulus of elasticity over 1 minus v squared, squared epsilon x plus v ey. So just to explain this, this is my stress at x. So I'm using modulus of elasticity for stainless steel, and our V is Poisson's ratio. So first I will solve for Poisson's ratio, which is, I will utilize, where should I'll do it right here. So do it out of the way. So my Poisson's ratio, V equals negative epsilon y over epsilon x. And I just plug in these two values, which I know. It is, so Poisson's ratio, V, negative EY, EX. So my EY is negative 1.916 times 10 to the negative 4, and this is negative, so negative is going to make it positive at the end. So 4 to 7, 5 times 10 to the negative 6. My V will end up being 0.404. So now that I know my V, I can plug in my modulus of elasticity, which is right here. Also, at the table, they give us some PSI, and we want it in terms of KSI, which is stated in the problem. So if you convert these, this will be 28,000 KSI, and this would be 10,800 KSI. So now we can begin plugging in. So 28. Got confused there. Modulus of elasticity is 28,000 KSI. 1 minus 0.404 squared. And then our EX is 475 times 10 to the negative 6 plus Poisson's ratio, which is 0.404, and that is negative 192.10 to the negative 6, and I will plug that into my calculator really quick. So if I plug this in into my calculator, that's just kind of clear. So X is gonna be 13.29. Now that we know our X, we can do the same thing and we can find sigma Y, which is our state of stress at Y. So at Y, we use the same equation, except our values flip. So it is EY plus EX. So here, I'm gonna plug in my values. So 28,000 over 1 minus 0.404 squared. Here it's gonna be negative 192. Sorry, looks like there's a decimal point there, but there isn't. So 192 times 10 to the negative 6 plus 0.404, 475 times 10 to the negative 6. And if you plug all that into the calculator, this will be negative 0.0033. Now, we found our state of stresses. Now we need our shear strain, which is our TXY. This is just the E modulus of rigidity, which is G times our gamma XY. So if I just plug in these values, our modulus is from the table, and it's 10,800 KSI times, and then we found our gamma xy, and it is negative 5.196 times 10 to the negative 4. And then if you plug that in, your txy is going to be negative 5.612 ksi. So we will utilize these for our Morse circle. So these two are our bounds, and then this is how much it can, when it our stresses. This is our here, I'll just draw it out. I will draw out a Morse circle, so I'm gonna need my x and y axis. It is not going to be drawn to scale. It's just gonna be really quick. So our sigma y is somewhere over here, like very close to the x-axis. I mean, the y-axis. So this value is 0.0033 negative, and then my not max, our x is 13.29, and then this tells us how high the y-axis is. So approximately that. So there's going to be a positive 5.612, negative 5.612. So how you graph this is you're going to graph your sigma x negative tau xy and sigma y tau xy. So our value of x is 13, and we know our tx value is negative, so negative is going to be positive. So we're going to plot this up here somewhere. Here we have our y, which is negative, and then we have this value, which is a negative. Actually, it's gonna, yeah, somewhere right here. But I'm gonna rewrite my negative 5.612 on this side just to be legible. So using Morse circle, you can connect these two dots. And then here you can draw a circle, and my circle is not going to be super exact, but I'll try to make it as intersect as much as possible. So if I draw my circle, this should actually, I'm gonna put it here. It's supposed to intersect. From here, from using Morse circle, we can find our principal stresses, which is our sigma 1, sigma 2, and that's what we're looking for. So first, we need to find at what point does this intersect. So we need our midpoint, and if we plug this into a calculator, so it's gonna be, the equation is gonna be to take our what do I call it, midpoint. I'll just put, this point is my y plus my x over 2. So if I do this to find my midpoint, I just plug in 13.29 plus, I have a negative value of negative 0.0033, sorry. 0033, divide that by 2, and I get, let me plug that into my calculator really quick. So 13.29 minus 0.0033 divided by 2. This gives me 6.64. So that is my, I can go one more. That is my midpoint. So 6.6643. So now that I know my midpoint, I need to know what this distance is. So I'm going to subtract this. I'm going to subtract this number by this number. So 13.29 minus 6.643. This is a value of 6.647. So I know my x, I'll just call it x, and my y. So I can use Pythagorean theorem to solve for my radius. So using the Mohr circle, my radius is equal to square root. I have 6.643 squared plus, and then I have my height, 5.612 squared. This will give me 8.69, which I'm just gonna call it 8.7. From here, it's very simple. So my sigma 1 is my midpoint, my 0. So from here, well, first I need to explain my sigma 1, which sigma 1 is right here. It's this value right here, and my sigma 2 is this value. So basically what we did is we found the distance of this r right here. So we need a we found the distance of r, which I'll draw this out just to be clear. This is r, and having that value, this is our midpoint, 0. So, or basically it's our 0. So we need to add that. So 6.643 plus what we found with the radius, which is 8.7. And this will turn out to be 15.343. And that's my value at this point, which is the max. And then for our min, which is this 2, this is this value. So it's the same thing. It's our distances over here are the same, or r is the same. So we just need it to find our min. So use the same midpoint, except you minus 8.7, and that gives you negative 2.057, and these are all in KSI. So these are my principal stresses, my 1 and my 2, my max and my min. And then to find our shear stress max, which is tau max, is just this, what we found our R, 8.7 KSI. And that is how you find your sigma 1, sigma 2, and your top max. So this is my principal stress, these two, and then this is my shear stress max. So just to recap, um, referring back to the flow chart, we started off with our strain gauge data, which was given. We use our Rosette equations to find our state of strain at X and Y. So X, Y. And we also find our gamma XY, which was our shear strain. And this helped us find our shear stress at X and Y. So these two helped us find our stresses at state of stress at X and Y. And then from here, we utilize Mohr circle to find our principal stresses, which is our max and our min, and our stress, strain, or shear stress, sorry, max. And this is my signature. And that is all. Thank you very much.